Firewalls are a system that has rules to control inbound and outbound traffic on a network. In this section, we are going to learn about some of the different types of firewalls that can be deployed on a network. Firewalls are used as an enforcement point between trusted and untrusted networks. So if you only want to allow email and web traffic to an untrusted network, then you would configure a firewall with rules to only allow those types of applications. Firewalls are most commonly used between internal networks and the internet. So when you get a router from your service provider or from the computer store, it's typically going to have firewall capabilities built into it. So as your gateway device facing the internet, it'll help to prevent traffic from getting onto your network from the internet. One of the main jobs for a firewall is to know where traffic is sourced from. So if I go to google.com from my home network, my firewall is smart enough to allow the return traffic back through the firewall to my computer. But if something was sourced from the untrusted internet towards my home network, the firewall would block the traffic. Proxy firewalls can be used in the forward or reverse direction. Traffic is redirected to the proxy firewall for inspection. Proxy firewalls are useful if you need to control traffic within a point in the network that does not have an inline firewall. Application firewalls have the ability to control traffic at the application level. With how dynamic traffic is nowadays, and with all the different types of application firewalls are required for deep inspection to block or allow traffic at the application level. Personal firewalls are applications running on computers that can be configured for IP and program rules. Personal firewalls are so important because users may not always be protected by a central firewall on a network. So as long as the user at least has their personal firewall running, they at least have some type of protection on any network that they join. Firewalls can be stateful or stateless. Stateful firewalls keep track of the state of connections, while stateless firewalls do not, making stateful firewalls the preferred option. Firewalls can be a closer eye on what is traversing its zones when it can keep track of connection states. State tables are used to track the current state of each connection. This allows the firewall to permit or deny traffic based on if a connection is established and from where traffic originates from. With firewalls, a TCP connection is considered to be established after the SYN, SYNAC, and ACK exchange is completed during the TCP three-way handshake. With stateful firewalls, if a connection is sourced from a trusted zone to an untrusted zone, the return traffic is permitted since the connection is in the state table and was initiated from a trusted zone. However, if traffic was sourced from an untrusted zone, like the outside, and there is not a rule to permit the traffic inbound, then the traffic will be denied. Cisco ASA firewalls are at the core of the Cisco Security Suite. In this section, we are going to learn about most of the Cisco ASA firewall features. Here's a list of some of the ASA models that are available today. From home and small business models all the way up to enterprise 5585Xs, the ASA product line has a lot of models to choose from. Alright, so now for the fun part. We're going to start configuring an ASA in the lab. But the first thing we need to do is to connect a console cable to the ASA's console port. This will allow us to serial into the ASA for the initial device setup. As we learn ASA command line, you will come to find that some of the CLI commands are similar to iOS switch and router commands, but for the most part, it is like learning a new language and can take some time to get used to. Let's start by configuring some basic settings. When you log into an ASA for the first time, you're going to be at this prompt. If you type enable and just hit enter, it'll get you to the privilege prompt. ASAs do not have a enable password by default, so you just hit enter. We're going to say no for anonymous error reporting. And now we're ready to start configuring our ASA. Our main objective at this point is to get it ready to be managed over the IP network. So we're just going to configure it enough to where we can manage it remotely. And then once we can SSH or HTTPS to the firewall, then we can make the majority of our configuration changes. So we'll give it a host name. For SSH, we of course need a domain name. Then we'll add our local user accounts that we'll use to log in for console, SSH, and HTTPS access. In the real world, I would not recommend using Cisco as your username. I'm just doing it that way in the lab to make it easy. And I'd probably use a better password than super secret 123. Now we'll enable SSH. We'll set it for version 2. And then we have to configure what networks we're going to allow to access the SSH terminal. So this is the same as doing like a VTY access list on our iOS routers and switches. And you see that I have management after my networks. Well, you have to specify the name of the interface, which we'll get to later on. So HTTP is HTTPS access. We enable HTTPS access with the HTTP server enable command, and then of course we have our HTTP network access. Here we're going to set our AAA authentication parameters for SSH, HTTPS, and console connections. Specifying the local keyword says that we're going to use local user accounts. Then of course we want to make sure our time is accurate, so we'll set our time zone information. One thing that's weird with ASAs is to look at our IP interfaces, it's show interface IP brief instead of like routers and switches, which is show IP interface brief. So here's the IP interfaces that we have available for us to configure. On the lab, you'll see that there's actually a dedicated management port on the bottom there of management 00, and that's the port we're going to use for our management connectivity. Say show run interface just to see what it looks like. So it's set to management only. So management interfaces, you can say management only on the interface to make it only allowed for management communication. And then we'll learn more later when we configure our non-management interfaces that the name if command is required to assign our interfaces to security zones. So this is saying this is part of the management zone. And then of course we have a security level that defines what traffic is allowed between different interfaces based on their security levels. We'll give it an IP address of 10.0.2.10/24. That's our management network. Make sure we can ping our gateway when we can. So we now have basic connectivity out of our management port. I like to set the management security level to 99. So we see we have no routes currently, so that we can access our management network from different networks. We're going to add a static route out of our management interface to the LAN. So with ASAs, instead of IP route and then the network and next hop, you say route, the name of the interface that you want to use to route out of, then the destination network and next hop. So it's a little bit different than we're used to for switches and routers. A few more things we want to configure for the initial setup to follow some management best practices. We want to make sure that we have logging enabled. I like to set my logging level for my buffer to debugging. and then my logging trap to log to a remote syslog server to informational, and then we'll point to a remote syslog server out of the management interface for remote logging. So that's really critical. You want to make sure that your firewall not only has local logging set up, but also remote logging, so you can troubleshoot network or security issues. Then we want to make sure we have accurate time for correlating events. So we'll make sure that we synchronize to a NTP server so our time is always accurate. Then I like to turn off SNMP services if I'm not using them on my firewall. Obviously that can be a big vulnerability. And then we'll throw a banner on there as a warning to unauthorized users. So now that we have an IP address configured on our management port, we should be able to remotely access the firewall via the SSH protocol with our PuTTY application, or via HTTPS with the ASDM application. ASDM is a GUI application that you can use to manage your firewall, and if you're not big on using the command line, then it's a great option for configuring and monitoring the firewall. So we'll launch our PuTTY application that you can download for free from the putty.org website. Put in the IP address of our firewall and log in with our local username and password, and we should have SSH access to the firewall. So here we go. Enable, put in our enable password, and now we are connected over the IP network to our firewall. The first thing I like to do is to upgrade the firewall software. First, you want to run the dir command to look at our directory. In the ASA's disk 0 is going to be where you're going to store your software images. So I like to make sure that we have enough space on the firewall first. So it looks like we're good on space. We'll run show version just to see what our current version of software is, to get an idea of how big of a jump we're going to make. Depending on the software version, you might have to do multiple software upgrades instead of going directly to the version you want to be on. But we're running pretty new software here, so I think we're good as far as that goes. I'm going to go to Cisco's download page and just type in ASA. Then I'm going to select the ASA model that I'm running in the lab to make sure I select the right software image. Then we're going to download the device manager software. I'll just grab the latest version of it. So this is the ASDM image that we can download from the firewall to manage it via HTTPS. So we'll take that. Then we'll go back to the other ASA images, and we're going to download the ASA system software image. Now that I have my images downloaded, I've placed them in my FTP folder, and I'm going to copy the images from my FTP server over to my disk 0 directory on the firewall. And then after we copy the images over, we'll tell the firewall to use the images on boot up to upgrade the software. So copy from my FTP server to disk 0. Let that run. There we go. Now the main ASA image has been successfully loaded to the firewall. Now we'll load the ASDM image to the firewall that we also downloaded. Now we have both of our images on the firewall. One thing I like to do is to check the MD5 hash on the software image that I uploaded to the firewall and make sure it matches the hash from the download on the website, which you were able to see that by hovering over the image on the website you can get the hash. So I like to paste the hash in on the command line, and then if you run verify MD5 and then the path to the image, you can have it do an MD5 check and just kind of eyeball and make sure that the hash looks the same. So my hash looks good, so now I know my software image is not corrupt from the image upload to the firewall. So now we have to tell the firewall to use our new software. So we're going to say boot system and then the path to our main ASA image. And then we're also going to have to tell it to use that ASDM image. So we'll say ASDM image and then the path to the ASDM image. So now our software is uploaded. We told the firewall to use the software. We'll save the configuration and then reload the firewall. And then once it boots up, it should load the new software and be upgraded. So after about 5 minutes or so, your firewall should be booted. You can get a ping going to it just to know when it's actually back online. So now I'm able to successfully SSH back into it. And then when we get into it, we're going to want to run show version to verify if we're running the new software. So we see that we are indeed running the new software that we wanted to upgrade to for the system image and ASDM. Now we're ready to install the ASDM software to gain GUI management of the firewall. To download the ASDM application, you can actually HTTPS to your firewall. Once you connect, you'll be able to download the ASDM software right from the firewall. So we'll say install ASDM. It makes you authenticate, so we'll put in our local username and password that we added to the configuration. Then it's going to ask us to run or save the application. We'll run it. Hit run again if you have to. Next, and install. It does rely on Java, so if you do have issues, you may have to upgrade your Java application. I actually already have the application installed, so I'm just going to launch it, put in the IP address of our firewall, and then our username and password to connect to it. Alright, so our ASDM is loading. And now, here we are in the ASA ASDM application. So that looks good. Now we're ready to proceed with our more advanced configuration tasks. Now that we have our software upgraded, we have basic IP connectivity to the firewall via SSH and with the ASDM application. Now that we have some basic settings configured on the ASA, we can start to provision it for the interfaces that will be connected to the firewall. Most firewalls at a bare minimum at least have an inside and outside interface. These zones are created with the nameif interface commands. Once the zone names are set, then security levels are required to let the firewall know which zones are trusted and untrusted. The security level range is from 0 to 100. The lower the security level, the less trusted the zone is. So we always want the internet-facing zone to be set to 0 and the internal-facing zone to be 100. Security levels control where traffic can be initiated from. So for example, by default, all traffic from a security level 100 interface would be allowed to talk to a security level 0 interface. The opposite holds true for a lower security interface to a higher security interface. So if traffic is sourced from a level 0 zone destined to a level 100 zone, it is denied by default, unless there is an access list rule that permits the traffic. Next, we of course need IP addresses assigned to the zone interfaces to be able to provide IP connectivity. Finally, we need to add a default route using the outside zone as the egress interface so that the inside zone can route through the firewall and access resources on the internet. Now we'll jump back into the lab and we'll provision our lab ASA with these interface parameters. Alright, so we'll go to configuration mode, paste in our interface script and our default route. So you'll notice that when we named our outside interface outside, it said that the default security level for interfaces named outside will be set to 0. And then anything with inside is set to 100. So by default, the firewall is smart enough to know what security levels to set interfaces to based on your name. Just to show you, if we named an interface DMZ, it would by default set it to a security level of 0. DMZ should actually be set to 50. This way the DMZ can talk to the internet, but it can't talk to the inside. Since you're typically going to have public-facing devices in your DMZ, you want to keep it in between the inside and outside. So now that we have our interfaces configured, if you do the command show interface IP brief, I can see my outside and inside interface. We'll go ahead and enable those with the no shut command, just like we would on a switch or router. Looks like they're both up. I like to run the command show run route to look at my static routes I have configured. So we have our default route going to our provider next hop. Let's make sure we can ping our provider next hop. And we can. Then we'll see if we can ping the internet. And we can, so now we have internet access out of our outside interface. We're not going to be able to browse the internet yet from the inside because we haven't set up any natting, which will be configured in a later section. We don't have any routes to the inside in this lab. In the real world, you would probably have some type of route to the inside. So in the lab here, we only have one connected network to our inside interface. In a big network, you would have a core that has all of your gateways, and then the core would have a default route to the firewall, and then the firewall would have an inside route with the core as the next hop to get to all of the internal networks. You can also run the command show route, the equivalent to show IP route on a switch or router, and you get the same output that you would get on a switch or router, just a different command to get your route table output. Now let's take a look at what our interface configuration looks like in ASDM. Right from the home page of the ASDM application, you can see your interface status. We have our inside, outside, and management interface here. You also get a traffic counter as well as the link up-down status. If you go to configuration and then interfaces within the device setup option, you can manage your interface configurations from here as well. If you hit edit, you can change the IP address, enable or disable the interface, and even change parameters like speed and duplex. We even have the ability to add brand new interfaces from this page. So we would first select the physical interface. We could assign a VLAN tag if we wanted to do sub-interfaces, and all of the other interface parameters. You can also do some interface monitoring from the ASDM. If you click the monitoring tab and then go to interface graphs, if we select an interface, we have all of these different graphs to choose from. No firewall would be complete without access lists. Typically, ASA access lists are going to just be inbound and on the outside zone interface, mainly to override the security level default drop actions to permit traffic to public-facing services within a DMZ. Best practice with firewall ACLs are to only allow what is necessary. So for example, if you had a web server in a DMZ that needs to be accessed from the internet, then you would only allow web ports like HTTP and HTTPS in the access list. So here you can see the example configuration. We're adding a DMZ interface to our lab ASA with this access list configuration, just to show you how you would typically use access lists in the real world. So here in our access list example, we have our access list entries that say what is permitted or denied in the access list. And then to actually apply the access list, we assign it to a zone with the access group command. Now we'll go to the lab ASA and apply these configurations. Okay, so we're in the lab ASA. We'll paste in our DMZ interface and access list script. So I'll just say show run interface G02. So we now have a DMZ that we can utilize for our lab configurations. I'll enable that interface. Okay, so now we have this outside access list. I like to run the command show run access list. So here's our access list entries. One thing that's hard to wrap your head around when you go from configuring access lists on routers and switches to firewalls is that you don't assign the access list to the actual interface. We're assigning it to a zone. So if you run the command show run access group, you can see which access lists are assigned to your zones. So with this access group command, we're saying apply this access list name inbound on our outside interface. So when traffic is sourced from the internet, from the outside of our firewall, destined to this IP address in the DMZ, it's going to permit TCP traffic destined to port 80 and 443. And then all other traffic will be denied. To configure access lists in the ASDM, again we go to the Configuration tab, Firewall, and then Access Rules. And you can see the ACLs that are laid out for each interface. Typically we don't care about traffic sourced from the inside entering the firewall. Our main concern ends up being for things coming in from the outside, destined to our firewall's public interface. So we see we have 3 rules on our outside. First, we're permitting traffic destined to our web server for port HTTP and HTTPS, and then we have a deny any at the end of our access list. Even if you didn't have a deny statement in your specific interface rules, there is a implicit deny, just like for a router or switch access list. You can see down below you have a nice visual representation of what the access list is accomplishing. And this can really help when you're trying to visualize what direction your access list will have to be applied to. Private IP addresses are not routable on the global internet. Network address translation can be used to translate private IP addresses to global, routable public IP addresses. NATs are a very important part of security. As a network security engineer, NATs are a huge part of daily configurations and troubleshooting. In this section, you are going to learn about the different types of NATs that can be configured on Cisco ASA Firewalls. Static NATs are used for one-to-one mappings between IP addresses. This is the type of NAT that would be used for public-facing services like web servers. Most companies own a block of public IP addresses that are allocated for public-facing devices. So if I need to make a FTP server reachable via the internet, I would pick a public IP out of the range I own and configure it as a static NAT to the private IP address of my internal FTP server that is secured behind a firewall. The newer, most common way to configure static NATs is something called object NATs. With object NATs, we're creating IP address objects for the public and private IP addresses that are used for the NAT, and then the network object that defines the internal private IP address, we add our NAT statement within that object. Let's talk about how this NAT configuration works. So you'll notice that after the NAT command, we have DMZ, outside. That's defining the source and then destination zone for this traffic flow. So when traffic goes from the DMZ zone to the outside zone, this internal host IP will be the original source, and its translated source will be this web outside public IP object. And going in the other direction, the opposite is true. So if traffic were to be sourced from the outside destined to our outside object, which would be the original destination, the translated destination would be our inside private IP address object. We're back in our lab ASA Firewall. To configure our one-to-one NAT, first we're going to configure our objects for the public and private IP addresses that will be used for the one-to-one mapping. So I ran show run object to show all of my network objects I have configured. So we have our outside object that is tied to our public IP address, and then we have our inside object tied to our private IP address for our internal server. And these network objects that we have here, they can be used for more than just NAT configurations. They can also be used for configurations like access lists. So instead of writing access lists based on IP addresses, we can actually base them off of objects. Now we'll configure NAT for our inside object. And since this IP host is a part of the DMZ zone, I'm going to want to reference that zone in my NAT configuration. So here, within the inside objects configuration, I've added this NAT rule. This rule is saying that we're going to NAT traffic for this object that sources from the DMZ zone, destined to the outside zone, to this web outside object address, which of course is our public IP address. And then as we mentioned previously in this lecture, the reverse is also true. So anything destined to this object, sourced from the outside, destined to the DMZ, will be translated to this IP. We can run the show run NAT command to see all of our configured NATs. And then for verification, we can either run show NAT or show xlate to see some statistics on our configured NAT rules. Next, we have dynamic NATs. Dynamic NATs are typically used for outbound user connections to the internet. A pool of public IP addresses can be configured as a NAT pool that can be shared by multiple sources. Each new connection through the firewall can use one of the IPs out of the NAT pool. The issue with standard dynamic NAT pools is that only one public IP address can be used at a time. So if a single host needs more connections on the internet than the amount of addresses that are available, then the pool of public IP addresses would not be sufficient. To configure a dynamic NAT on an ASA firewall, you can create a NAT pool with a network object, which would typically be a range of public IP addresses, and then you would create an inside network object for the subnet that would be utilizing the NAT pool. And then of course we add our NAT command within that object. I'll paste in our script into our firewall. So now we have our new object for our NAT pool, and then the network that resides on our inside zone is defined by this object. We run show run NAT. We see that now, in addition to our one-to-one NAT for the DMZ zone, we have a generic NAT for inside users to use so that they can be NATed to public IPs for internet access. The key thing to understand with the dynamic NATs is that it doesn't matter what IP the inside hosts get NATed to, because nothing on the outside needs to point directly to the inside hosts. So unlike the one-to-one static NAT mapping, we can dynamically be NATed to random public IP addresses as long as the return traffic for the inside initiated connection makes its way back to the firewall. That's all we care about. To solve the limitation of dynamic pool exhaustion, PAT, or port address translation, was introduced. PAT has the ability to use port numbers in addition to IP addresses for its mappings. A single public IP address can accommodate over 65,000 NATs instead of only one when compared to dynamic NAT. Each NAT is mapped to the first available pool address with a dynamic port number. These port number to IP mappings are tracked in the NAT table so that the NAT device can send the return traffic to the correct host. When one of the IPs of the PAT pool has exceeded its limit of port translations, then the next available IP in the pool can be used. PAT is the most common method of NAT for allowing internal user devices to access the internet via public IPs, and this is what you would see in the real world. To configure a dynamic PAT on an ASA firewall, it's actually the same concept as a dynamic NAT, except we have the PAT pool keyword after our dynamic statement in our NAT line within our inside object. So we'll go in and paste in our PAT pool. So you can see that with our dynamic NAT, it looks almost the same except we're missing the PAT pool command here. This is what defines the NAT as being a port address translation pool. Our last type of NAT is policy-based NAT. Policy-based NATs translate addresses based on policy rules. Conditions like destinations can be used to determine what address will be used for the NAT. For example, if you look at our NAT table here, we have it so if an inside source is destined for the IP address 4.2.2.2, then we'll translate the source to our .12 address. And then if an inside host is destined to 8.8.8.8, based on that condition, we're going to translate the source to the .13 IP. So now you can see how you can choose which translation to use based on certain conditions. Here's an example of a policy NAT configuration for an ASA firewall. So this NAT's saying when we have the original source of this inside object, the 10.1.10.0 network, we're going to translate its source to the network object IP12 if this object is the destination. And then the same goes for the second line, except it's a different set of objects. So there we go, we pasted in our script. We have all of our new objects and then our policy NAT defined. Alright, now that we've got to see the NAT configuration from the CLI, we'll log into the firewall with ASDM and look at the NAT configuration in the GUI. So we'll go to Configuration, Firewall, and then NAT Rules, and now you can see what our NAT rules look like in the ASDM. So one important thing to know is that in the order of operations, it's going to be top down. So our object NATs are going to be at the end of our NAT rules, with our single line NAT configurations up at the top. One thing cool about the ASDM is you can use this packet trace feature, and we can say, okay, for this source IP going to this destination IP address and with these port numbers, what would happen to this traffic flow if it went through the firewall with our configured rules. Hit start. And we see it checks the route lookup, the NAT configuration, and the IP options. And we see finally that the packet would be allowed if it went through the firewall. And then if we hit this NAT drop down option, you can see the NAT that this traffic flow would have matched. So we see that just as we would expect, we would match our last catch-all NAT rule for our dynamic PAT. ASAs can operate in two different modes, routed and transparent. Routed mode would have layer 3 interfaces, while transparent mode would have layer 2 interfaces. 99% of the time, I see ASAs in routed mode, and it is not as common to use transparent mode. A use case for transparent mode would be if you had a LAN segment that you wanted to inspect traffic on that had no routing capabilities, then you could use transparent mode to enforce traffic at a layer 2 level. Routed mode is the default mode. To switch to transparent mode if you need to, you would use the global configuration command firewall transparent. ASAs can be broken up into multiple logical firewalls if they are placed into multi-context mode. When ASAs are in multi-context mode, one physical firewall can allocate specific interfaces to multiple logical firewalls. For high security networks, it may be required to force certain networks through dedicated firewalls for additional security. To enable multi-context mode on an ASA, you enter the command mode multiple. Then, after the ASA is restarted, it will operationally be in multi-context mode. Once in multi-context mode, there is a system configuration mode that is used to manage contexts and interface allocation. Once contexts have been created in system mode, you now have multiple virtual firewalls running on one physical appliance. You can access each context configuration by entering the command change to context and then the name of the context. Once you change to a context, you can manage the virtual firewall configuration. For example, if you wanted to add an access list to your finance virtual firewall, you would change to that context's configuration and then configure it just like you would a completely different firewall. In addition to the contexts that are added within the system configuration, by default, an admin context is created. The admin context can be accessed by entering the command change to context admin. The admin context configuration is used for management features like AAA, SNMP, and logging. To switch back to system mode, you can use the command change to system, and that'll take you back to the base configuration prompt. Here we are logged into one of our lab ASAs that happens to be running in multi-context mode. You can run the command show mode to confirm your firewall's mode, and as you can see, we're in multi-mode. There is certain licensing that is required to run in multi-context mode. If you run the command show version on your firewall, you can see how many security contexts your firewall is licensed for. So for this one, we could have up to 5 logical firewalls. So currently we're in the system mode. If we enter the command change to context admin, that now takes us into the admin context. Go back to the system mode. Alright, so for this lab, we're going to create a context. We'll go to configuration mode, and we'll say context, and then the name of our context. We'll just call this context lab. And now we've created the lab context, and we can now allocate interfaces to the context. Allocate interface, the name of the interface, which is G2. And now if I run show run context, we see that we have our admin context, this test context from an earlier lab, and then our lab context. I'm actually going to delete this test context. Now that we've created this context and we have an interface assigned to it, we can go and configure the context by entering the command change to context and then the name of our context, which is lab. I missed one important step. When you create your context, you have to give it a configuration URL. So that's where it's going to store the context configuration. Now that I have my config URL applied to the context, I can now switch to the lab configuration. If we say show run, it has some default settings, and then you'll notice that we have this interface within our context configuration that we can modify. So now you can see that you only can configure interfaces that have been allocated to your context. And then I'll switch back to system with change to system, and then we can go back and start to create more contexts. Modular policy framework is a method for applying different security features with class maps and policy maps, similarly to applying QoS and zone-based firewall configurations on a iOS router. Once traffic is matched with a class map, a policy map is used to apply traffic policies like application inspection, quality of service, and IPS redirection. ASAs by default have a modular policy framework configuration. We can run the command show run class map and show run policy map to see our existing modular policy configuration. So this default list is basically saying match all traffic, and for that default class of traffic, we want to apply these inspection rules. I usually don't tweak too much stuff in my policy maps. The main reason in the real world that I adjust these are if there's issues with certain protocols, like we usually want to turn off ESMTP inspection because it can break email services, so we'll go ahead and shut that one off from its additional inspection for that protocol. I've had to disable the skinny inspection, and outside of adjusting the default inspection rules to fix application issues, then I'm usually adding a class map to redirect traffic to a NetFlow destination or for an IPS sensor. And if you want to confirm matches on your policy map, then you can run the command show service policy. To configure the modular policy framework in the ASDM, we go to configuration, firewall, and then service policy rules. And this is where you'll find your policy map and class map configuration. And just like I showed you in the access list video, if you click this diagram button, you can see a visual representation of the policy map actions. In active standby mode, one ASA is active operationally. Configuration and connection state changes are replicated to the standby ASA for stateful failure recovery. If an active ASA fails and goes down, the standby ASA will go active and take over the role as the primary ASA. One important thing to understand about high availability ASA firewalls is how they need to be interconnected. Each firewall must have the same zone interface connections. This is required so that if a firewall were to fail, it still has the same physical connectivity as the active firewall. In addition to our zone interfaces, firewalls must have what's called a LAN failover interface. This interface is used for hello messages between the firewalls so that both firewalls know the status of their peer. It's also used for configuration, replication, and synchronization, so if a configuration change is made on the active firewall, it can use this interface to replicate that change to the standby firewall. In addition to the LAN failover link, you can optionally have a state failover link. This link is used to pass connection state information so that the standby firewall can support existing connections that were previously on the active firewall. The state failover link should be a dedicated link separate from the LAN failover link, but it can use the same link as the LAN failover link. So you could add both of these failover roles to a single link between the firewalls. Before we configure the actual failover commands on our firewalls, we want to have standby IP addresses assigned to all of our interfaces. This IP is pushed to the standby unit and can be used for interface monitoring between the primary and secondary firewalls. It can be any available IP address on the interface's LAN. If possible, you want to make it the next available IP address after the primary IP. To configure failover between our ASA firewalls, we have to configure failover parameters on the active and standby firewall. The first step is to enable failover globally. Then we define which unit will start off as the primary firewall and which unit will be the secondary firewall. Then we have to assign an interface to be a LAN failover link. Then there's some timers. You want to have a failover key for security. The failover replication HTTP command is what enables state replication for HTTP traffic. Then we define our stateful failover link, which we're going to follow the best practice in this lab and have a dedicated link for LAN failover and a dedicated link for state failover. And then IP addresses are required for the communication between the LAN and state interfaces, so we need to assign IP addresses for those interfaces. And these can be non-routable networks because the layer 3 communication is only going to exist on your directly connected interconnections between the firewalls. Now we'll jump into the lab ASA firewalls to configure active standby failover. Okay, so we'll start on the firewall that we consider to be the primary out of our two firewalls. We'll paste in our failover configuration. After you paste in your failover configuration, you may lose connectivity to the firewall as it goes through its negotiation to see if there are any other HA firewalls connected. I'm logged back in and I ran the command show failover history, and you can see from the time I pasted in the failover configuration, you can see the different states the firewall went through while it negotiated. Next, I want to add secondary IP addresses to all of our IP interfaces. Run the command show run interface. I have a standby IP assigned to my management address, but now I'm going to want to go through and add standby IPs to all my active IP interfaces. I'm just going to pull up a notepad, paste it in, and then I'm going to use the next available IP address. Then we add the command standby and the IP address. .2, and then we'll use .2 on this network too. When you configure failover, if you start with the firewall that's considered to be the primary, you'll just add your standby addresses to its configuration, and now our primary firewall is configured. Our second firewall that we add to the failover pair would be considered to be our secondary firewall, and since we already configured these interfaces on the primary, we don't have to configure any of these IP interfaces to the standby firewall. It'll retrieve these parameters through synchronization once it communicates with failover to this primary firewall. Okay, so on the secondary firewall, we'll configure failover globally. Define this unit as being the secondary unit. I'm going to say failover. We'll define our LAN interface. That's going to be gig 07. Configure our state link. As soon as I added the LAN failover IP address information, the firewall started to run their discovery process and were able to detect each other. So you can see that this firewall detected the active mate, which was the primary firewall that we previously configured. And then it started to retrieve configuration replication from its active mate, so the primary firewall. So now you see our host name changed automatically. And if we run show run, you see that it's retrieved the full configuration sync from the primary. We'll log back into the primary firewall now, and to verify our failover status, we can run the command show failover. We see that the host that we're currently logged into is considered to be the primary and active firewall. That's what it should look like normally. And then our secondary unit is standby and ready. So that's exactly what we want to see on the secondary firewall. This tells me that we're running good and failover is configured properly. Once we have failover looking good, it's always good to test it. So we can actually run a command on the standby and tell it to be the active firewall, and then that'll force this primary firewall to be the standby just as a test, and then we'll switch it back. So I'll get an infinite ping going here to the primary firewall's management IP, and we'll see what happens and how quickly we fail over to the backup unit. So I'm going to run the command failover active on the standby unit. So this should tell the standby unit to take over as the active firewall. Of course, I'm going to lose my connection from that session. It looks like we did not lose any pings though. So now if I log into 10.0.2.10, so now I'm logged into the secondary that's now the active firewall, and I run show failover, and you can see that sure enough we forced a failover between the firewalls. So now the secondary units, the active, and our primary is standby. And we'll run the command failover active, and this will make the primary the active firewall again. And you can see that again we did not even lose a ping. So you can see how fast ASA failover works. And there you go. So now we're back to normal. Failover can also be monitored and configured from the ASDM. Right from the home page, we see we have a failover status section here. If you click the details option, it links you right to the monitoring page where you can monitor your ASA failover status. We can even send some commands to the firewalls right from here. To configure ASA failover from the ASDM, if we go to Configuration, Device Management, and then there is a High Availability and Scalability section. There's a wizard you can launch if you want to configure failover that way, or you can go to the failover configuration area. ASA firewalls can be configured with advanced firewall services for additional protection. Botnet traffic filtering is a service that can be enabled, along with a license, to protect against botnet and other suspicious activity. A dynamic database hosted by Cisco updates botnet-enabled ASAs with blacklisted domains. When clients try to connect to sites that match a site from the dynamic database, the ASA can log and drop the connection attempts. The latest and greatest ASA firewall services are classified as Next Generation Firewall Services. These services include IPS, URL filtering, and AMP. Now that Cisco has bought SourceFire and revamped their security solutions, all of these services are available on board Cisco ASA Firewalls. VPNs give us the ability to securely connect network devices over untrusted networks. VPNs are made up of security concepts like encryption, hashing, and authentication. There are two types of VPN access: site-to-site and remote access VPNs. Site-to-site VPNs are used to connect multiple networks between remote branch offices and data centers. These tunnels are formed between devices like routers and firewalls that have cryptography abilities. Remote access VPN is for individual remote users. VPN applications and secure web browser sessions can both be used on a mobile device like a phone or laptop to establish remote VPN tunnels. Now we will take a look at how an IPsec tunnel is formed for both types of tunnels. First, the traffic that needs to be encrypted must be defined. This traffic is called interesting traffic. You may only want to send certain traffic over the VPN tunnel. Interesting traffic is defined with an access list on the VPN gateway. Internet Key Exchange is the protocol used to set up security associations in the IPsec protocol suite. IKE is broken up into two phases. In phase 1, hashing, authentication, DH group, lifetime, and encryption are negotiated. Once the phase 1 policies have been negotiated, the peers run the Diffie-Hellman exchange to create shared secret keys. Then the VPN devices will verify their peer identity with authentication, and after these exchanges, a secure phase 1 tunnel is built for future communication. Next, phase 2 parameters like hashing, lifetime, and encryption are negotiated with transform set configurations. Then finally, an IPsec security association is created for the interesting traffic, and data can be encrypted and decrypted between the VPN gateways. VPN tunnels can be set to use two different modes, transport mode and tunnel mode. Let's compare the two. In transport mode, only the payload of the IP packet is usually encrypted or authenticated, and it requires less resource overhead. Tunnel mode is the default mode for Cisco devices. In tunnel mode, the entire IP packet is encrypted and authenticated. It is then encapsulated into a new IP packet with a new IP header. Once VPN tunnels are formed, there are a few different options that you should be aware of for the exam. The first is hairpinning. Hairpinning is when VPN traffic is routed back out the interface on which it was received on. This type of traffic flow is necessary for hub and spoke VPN topologies. Another important VPN option to know is split tunneling. Split tunneling is simply how a remote access VPN defines what is interesting traffic. An ACL is used to specify traffic that should be encrypted or sent in clear text. Remote access VPNs have many options to provide additional control to endpoint devices. Always-on VPN is one advanced feature that forces remote VPN access connections to always be connected to VPN. This allows enterprises to maintain constant control over company-owned assets. The last VPN option that you should know for the exam is NAT traversal. NAT traversal is used when a VPN connection is established through a NAT device. Normally, IKE uses UDP port 500, but with NAT traversal, UDP port 4500 is used. Remote access VPN used to be accomplished primarily with IPsec VPN client applications. This is considered to be the legacy remote VPN access option. Nowadays, SSL VPN is the way to go. One popular method of SSL VPN is clientless. With clientless VPN, no client application needs to be installed on endpoints. A user can simply launch a web browser, type in the VPN URL, and log right in from their browser. Once connected, all traffic is proxied through the VPN gateway through a HTTPS session. Let's hop into the lab and configure a clientless VPN setup on a Cisco ASA with the ASDM management software. When you're deploying a SSL remote VPN solution, the first thing you should do is get a real digital certificate. This is required so that remote VPN users do not get a certificate error when they try to connect. To get a valid certificate on our ASA Firewall for VPN, first we have to create a certificate signing request on the ASA. Once the CSR is created, we then export it and upload it to our certificate authority provider. Then the certificate authority will sign our certificate. We'll then install it back on the firewall, and we will have a trusted certificate to use for our VPN connections. To create our CSR, we go to Remote Access VPN, Certificate Management, and then Identity Certificates, and click the Add button. So we have to give it our FQDN name, our key pair size, and then we're going to save the CSR to a file locally on our PC. So we've successfully exported the CSR. Now we'll take that CSR, upload it to our certificate authorities website, have it signed. You'll want to open up the CSR in a text reader, copy and paste the CSR information onto your certificate authorities website. We'll then download the signed certificate and upload it to our firewall to complete the certificate installation. In addition to installing the signed identity certificate, we also want to install the root certificates of our certificate authority. Usually the root certificates from the provider will come with your identity certificate, or you can download them from their website. Now we have to tell the firewall to use this certificate on our outside interface. So we'll assign the certificate to the outside interface. Now it knows that it can use this certificate for HTTPS connections on the outside interface. Now we're ready to configure our clientless VPN options. So we'll launch the clientless SSL VPN wizard. Makes it really simple to set up your VPN. First, of course, we have to name it. Select the interface that will be active for SSL VPN connections. I always like to give my VPN configurations a group URL so that connections can be made directly to this policy with that URL. And we're just going to use local username and password for this, but of course you could use an external radius server if you wanted to authenticate to an external data store. Then we can make a new group policy for some of our configuration options. And there we go. So we've created our clientless VPN configuration. We have the connection profile and the group policy that was created. If you go into the portal configuration, you can do a lot of customization for the portal that is used by the SSL VPN users. You can customize it, of course, with what the title is and the image, the coloring scheme. You can set which applications are accessible by the VPN client. We can also go into our group policy configuration and set things like the home page that the user will get redirected to, and internal links that can be accessed directly from the VPN portal. Okay, so we'll test our clientless VPN connection. I put the URL to the Firewall's VPN interface in my web browser. You can see the web browser trusts the certificate. You can look at the certificate details and see that it was signed by GoDaddy. Put our local credentials in. And now we're logged into the SSL VPN portal. You see we have our link to our wireless LAN controller. We have options for SSH and terminal services. I'll go ahead and click on my wireless LAN controller link, test that out. So there you go, we are successfully connected to our internal wireless LAN controller with our HTTPS clientless session through our VPN gateway. You could launch an RDP session directly from the VPN portal. So there you go, we now have a remote desktop session that's being encrypted through our clientless VPN connection. To monitor and troubleshoot our clientless VPN connections, in the ASDM we can go to the Monitoring tab and then go to VPN, change the filter to clientless SSL VPN. Then we see our SSL VPN sessions. We can see the group policy that's applied to the user, the username and their public IP address. We can hit details here to get more information about the connection. In addition to ASDM, we can also go to the command line of the ASA and run the command show VPN session DB and web VPN, and you'll get a command line output of your clientless VPN connections. Next we have Cisco's AnyConnect VPN solution. AnyConnect is pretty amazing. You could spend a whole year playing around with all of the different features that AnyConnect has to offer. It is a client VPN application that can run on laptops and mobile devices. Unlike clientless VPN, data can be transferred directly between endpoints through the encrypted tunnel. So once you're connected, it is truly like the remote endpoint is connected locally to the network. Back in the ASDM, we're going to run the AnyConnect wizard just like we did for the clientless VPN configuration. Give it a name and associate it with an interface, which will of course be our internet-facing interface. AnyConnect can use SSL or IKE version 2, so you have the option here to select which protocols you want to be allowed for this AnyConnect profile. You have to select an AnyConnect image file. The AnyConnect image can be downloaded from the Cisco website and then uploaded to the ASA. We'll just use local credentials here, just like we did in the clientless VPN configuration. But typically you would have an external radius server being used for authentications. You need a DHCP pool for AnyConnect. The remote VPN clients will actually retrieve an IP address from this pool, and those IPs will be used to communicate over the VPN tunnel. We want to make sure that we exempt NAT translations for this traffic, also known as no NAT. And that's it, we've created our AnyConnect configuration. Now let's take a look at what that wizard is actually creating. First we have our connection profile. A good example of parameters you could assign with a connection profile are client address assignment and AAA. Connection profiles are also referred to as tunnel groups when you're in the command line configuration. Next we have group policies. A group policy is a set of user-oriented attribute and value pairs used for the VPN connections. Things like client configuration settings and filters can be applied with group policies. Split tunneling is where we define the traffic that will be sent through the VPN tunnel. You can either tunnel all VPN client traffic through the tunnel or define a split tunnel ACL to only use the tunnel for specific destinations. In this example, with our split tunnel ACL we've created, we're only tunneling traffic that matches 10.0 networks and 10.1 networks. All other traffic will be sent locally onto the user's local LAN. The last AnyConnect configuration options that I want to cover are client profiles. Client profiles are XML files that are stored on the AnyConnect VPN client devices with parameters like the name of the profile as it's shown in the AnyConnect application, always on VPN, and backup VPN gateway destinations. Each time a change is made to these profiles, VPN clients automatically receive any updates each time they connect. Well, now it's time to test our AnyConnect VPN connection. You first need to download the VPN client from the ASA or Cisco's website. I already have it installed on this computer. So here's the AnyConnect VPN application. We'll put in the URL that will connect us to our VPN gateway. And then since I have an alias set up, it gives me a drop down to choose which VPN connection I'd like to use. Of course, we want to use our AnyConnect lab configuration. Hit OK. And we've established a AnyConnect VPN tunnel to our ASA firewall. If we select this gear icon here, we can see some of the statistics for the VPN connection. We see the address we received via DHCP, the client profile XML file that we downloaded. Route details shows us what is actually included in our split tunnel ACL. These were added on because of a DNS option, but here's the 10.0 and 10.1 networks that we defined in our split tunnel ACL. To monitor and troubleshoot our AnyConnect VPN sessions, we can go to Monitoring, VPN, and just like our clientless VPN connection, we can see our AnyConnect connected clients. And we can do the same in the command line with Show VPN Session DB AnyConnect. One cool feature that can be integrated with AnyConnect VPN is Endpoint Posture Assessment with the AnyConnect Posture module. Endpoint Posture Assessment has the ability to scan an endpoint for things like antivirus and anti-spyware to determine if it's a compliant endpoint or not. If an endpoint does not pass the posture check, then it is denied access to the network or it can be remediated. An example of how you could use posture assessment would be if you only wanted VPN clients to be able to connect if they had up-to-date antivirus, or if you had secret files or registry entries installed on company assets that could be verified during the posture assessment. I happen to have the AnyConnect posture module running on my lab PC, and you can see that it's just layered below the core AnyConnect VPN module. If you click the Advanced Window button and go to System Scan, you can see the compliance information for the endpoint. The policy server is my ICE node, which is doing the posture checking. You can see which security products the endpoint assessment found on my endpoint. The posture assessment check that I have running is if my endpoint has FireAmp running, then it passes the posture check and is allowed to connect to the network with full access. In this video, we will establish a site-to-site VPN tunnel between an ASA and a Cisco CSR router. At Site A on the left, we have the ASA with an inside LAN of 10.1.10.0, and on the right is Site B with a router and local network 10.2.10.0. This tunnel will be configured via the command line on both devices. But then after we get the tunnel up, I'll log into the ASDM on the ASA and the Cisco Configuration Professional GUI management on the CSR so you can see how to use the VPN wizards if you are not comfortable with the command line. In the real world, we would always use the command line, but it can be a lot easier at times from the GUI. Here's our command line script that we're going to use on both the ASA and the router. You can see that there's some syntax differences between configuring it on the ASA versus the router. First, we will define our local and remote networks. This is considered to be our interesting traffic and is the only traffic allowed over the VPN tunnel. Then we configure a NAT rule to exclude translations between our local and remote LAN networks. When the VPN traffic egresses the VPN gateway's outside interface, without the NAT exclusion, traffic may match an existing NAT rule, which can cause issues with VPN tunnels. Next is the Phase 1 policy that defines the type of authentication, encryption, hashing, and DH group that will be used for the Phase 1 tunnel. We then need to create a pre-shared key that will be used for authenticating the VPN peers. On the ASA, the key is applied within a tunnel group, which is the same as a connection profile. Along with the tunnel group, a group policy is also required on the ASA. Next, we will set our transform set parameters for the encryption and hashing types that will be used for phase 2. To tie everything together, we need to create a crypto map. Crypto maps match interesting traffic ACLs, set our VPN peer public IPs, and define the transform set protocols. To activate the crypto map, it needs to be applied to an interface. This would normally be the outside internet-facing interface. Once the crypto map has been activated, you of course want to make sure that routing is configured throughout the network to send traffic to the firewall and out of the outside interface for traffic to be encrypted in the VPN tunnel. Let's start off with the Site A configuration on the ASA firewall. Okay, I'm in the lab ASA. I'll paste in our VPN script. Looks like it was happy with all of the commands. Now we'll head over to the Site B router and paste in the VPN script for that side. To start the tunnel, we need to send some interesting traffic across our devices. Here's a Site A device on the ASA side. Let's see what its IP address is. So 10.1.10.11. Now let's go and see what the PC's IP address is on the Site B side. The device over on the Site B side has IP address of 10.2.10.12. So we'll see if we can ping that IP from Site A. There you go, so that tells me that our VPN tunnel is working. Let's make sure that we can ping from Site B to Site A. Okay, so we have bidirectional communication. The first verification command I always run on ASAs is show crypto IceCamp SA. And that command is going to verify our phase 1 status. On ASAs, active is the state we want it to be in for a successful phase 1 tunnel. So we're active for the tunnel going to Site B. We'll run the same command on the Cisco router. The output's a little bit different. On routers, QM idle is the final state of phase 1, so it's not active like it is on the ASA. So this looks good. This shows me that phase 1 has been successful. Back on the ASA, to verify phase 2 and if traffic's actually being encrypted and decrypted across the tunnel, we run the command show crypto IPsec SA. It shows our local and remote network, our VPN peer IP. To truly verify if the tunnel is working correctly, you can tell if packets are being encrypted and decrypted. So this looks perfect. Run the same command on the Cisco router, and we have a similar output. We see our local and remote networks, our remote peer, and our encryption and decryption statistics. Now I'm actually going to delete the tunnels from the command line, and then we're going to configure the same tunnel but from the GUI management applications for the ASA and the router. So remove all of our commands on the ASA, and then we'll do the same thing on the router. Here we are in the ASDM on the ASA. To configure our tunnel from the ASDM, we'll use the VPN wizard for site-to-site tunnels. Put in our remote gateway's public IP address, outside interface, and then we can actually call out our objects that we created previously from the command line. Paste in our pre-shared key. We want to exempt this traffic from NAT translation. And then next, As you can see, it's so easy to configure site-to-site tunnels through the ASDM wizards, so this may be the preferred method for a lot of you. Hit finish. Okay, we should be good. Next, we'll use the Cisco Configuration Professional GUI management application on our Cisco router. Here's the Cisco Configuration Professional. It's a software that you can execute on your computer that allows you to manage your Cisco routers with a GUI application. So I've already added our lab router as a device. If you click on the configure button, you can see the different types of configurations that you can push to the router from the Configuration Professional. It's actually really cool. You can back up your configurations from here, upload files for software upgrades if you'd like. Okay, so now we'll configure our site-to-site VPN tunnel with the Configuration Professional wizard. We go to Configure, Security, VPN, and then site-to-site VPN. Launch the selected task. You can go through the quick setup wizard, but we're going to use the step-by-step wizard so we have the ability to customize some of the configuration. G1 is our outside interface. Put in our peer IP address and pre-shared key. By default, it has this 3DES policy. We're going to add a new one to match the security on the ASA side. We'll select that proposal and hit next. We also want to make a custom transform set. We'll select add. Hit OK. And next. Now we have to define our local and remote networks. Site B is 10.2.10.0 with a /24 mask, and site A is 10.1.10.0/24. So that's it. We've created our tunnel with the Cisco Configuration Professional. Click Finish and deliver the configuration to the router. Okay, so we should be in business. We'll go to our Site A PC and generate some interesting traffic to start the tunnel. And we're getting replies, so that's good news. Back on the ASA, if you go to Monitoring and Sessions under VPN Statistics, we can see the status of our tunnel. Up here you can see we have one active site-to-site VPN tunnel. Back on the router, we can go to Monitor IPsec Tunnels, and we get some of our Phase 2 statistics and a nice green icon if the tunnel is up.